Okay, can everyone see the right display now?
Yes.
Great. Okay, I am so sorry for that. I just was having some unanticipated technology issues, but let's see. I believe I've unmuted everyone on the Marquette team. Jenna, can you hear me?
Yes, I can.
Great. And Darren?
Yes, I can.
Garrett?
Yes, I can.
Great. Okay. So would you prefer I run your slides for you, or do you want to give it a try?
I can give it a try.
All right. Let's do that for you. Okay, Jenna, you should have controls now.
Okay. Yeah, no, it doesn't seem to be allowing me to change the slides.
All right, I'm going to run slides for. Oh, there you go. It's yeah,
very,
it moved.
very slow. Okay.
Sometimes it takes a moment, so apologies for that. And your 15 minutes begins now.
Okay. Garrett?
Hello, my name is Garrett Ward, and I'm with Marquette University Solar District Cup Team. Our district is New Mexico State University. The team members are Darren Garcia, Jenna Klobuchar, myself, Josie Ashfar, and Evelina Lasak. Our faculty's advisors were Dr. Tama and Dr. Ayman El-Rafai. An overview of what we will be discussing today is a summary of the team approach, a system design, and expectation operation, a summary of the deliverables, and a summary of the innovation and optimization.
So to begin, our team is comprised of 2 different sub-teams from 2 different schools. This was done through a cross-disciplinary partnership between Marquette University's Engineering Design course and the Milwaukee Institute of Art and Design, also known as MIAD's Junior Industrial Design capstone class. This allowed for us to focus on 2 different aspects of the project at the same time. The electrical design team from Marquette University were able to work on the system's technical design, including equipment selection, distribution impact analysis, and the financial analysis, while the industrial design team from MIAD was able to work on the visualization of panel placement, as well as the design of solar structures to be used on the NMSU Horseshoe Quad. On this slide, you can see juniors Josie and Evelina, who make up the industrial design team from MIAD, as well as seniors Jenna, Garrett, and myself, who make up the electrical design team from Marquette.
Next, we will be talking about our final system designs and the expected operation.
The equipment selection that the team decided upon, starting in the top left-hand corner picture, is the LG Neon R 360 watt solar panel, and then to the right is the SunGrow 60 kilowatt 480 volt AC string inverter. To the right of that is the Unirack mounting system that would be done on the ground mount and rooftops along campus. For the parking lot area, the team decided to go with a power parcel strategic grid carport. We would also have the cost of an inverter or of a transformer. And then for the battery reservoir that the team decided was to use GE reservoir storage unit.
Our design is broken into 3 separate parts. The first part is the ground mount system, which is located 3 miles off campus and near the geothermal substation. The final design utilized 94% of this land for the solar PV installations and the other 6% for the batteries. The area with the panels can be seen in the 2 labeled sections in the middle picture, and the area for the batteries in the back lighter yellow portion. The final system included 46,000 plus panels, 200 plus inverters, and 55 batteries. This added to a total PV system size of 16,400 kilowatts and a total battery system size of 55 megawatts. The system produced an offset equal to 68% of our given load data. The second system was focused on The campus. The area of campus for the solar installations that was allowed is outlined in red in the bottom picture. The top picture outlines the buildings and parking lots that we deem suitable for solar. We measured the feasibility of the land based on if the surfaces or rooftops were flat, had little to no obstructions, the max PV size that could be placed, and the amount of solar access or shading in that area. The final design included 12 systems consisting of 10 rooftop plans, some of which, like the science complex, included multiple buildings and 3 parking lots. The system totals included 26,000 plus panels and 167 inverters. The final PV system size totaled to 10,387 kilowatts, and this system produced a 55% offset of the given load. Here we show our 12 designs, with the parking lots in the third column being the carport systems and the others being rooftops. The carport systems we are utilizing is the Power Parasol roof style carport, which allows us to maintain full parking capacity and maximize energy production. The final section of our system designs include the challenge for our district, for which we were tasked to design an innovative structure that promotes the sustainability efforts of the university for the Horseshoe Quad, which is overlooked by the Chancellor's Building. We came up with 4 separate human-focused designs that are shown on the map. The map outlines potential placements for designs on the quad. The first design, which can be seen in the top left, is a pergola-style bench that is topped with the characteristics of the New Mexico state flag. The second and third designs resemble the traditional architecture of the New Mexico stone arches and can be seen in the top right and center. The final design is the bench that is in the bottom right-hand side, and this fuses both modern and traditional architecture with a stone adobe and wrought iron design in the back showcasing the sun. All of these designs include Maxion flexible solar cells that can be optimized to produce solar energy for small loads. The following is our system's expected operation for the combined ground mount and campus systems. The area used was 1,176,140 square feet. The equipment numbers are 76,489 panels and 404 inverters with 55 batteries. The total solar access across all installations averaged between 93 and 96% year-round, and the combined system offset equaled 119% of the load, and the total PV system size of 26.7 megawatts.
I will now provide a summary of the project deliverables. From the physical design, placement, and selection of panels, we then moved on to the system's theoretical response. We utilized irradiance data from the National Solar Radiation Database, as well as the provided university system load, to create a simulation of the solar PV system. Using the provided SAM system advisory model, we were able to generate the following graphs showing the system's irradiance, as well as the combined annual energy production. This revealed to us a total system size of about 26.8 megawatts and a battery size of about 55 megawatts. In modeling the system distribution impact analysis, we utilized 3 main programs, including OpenDSS, which is used for systems impact modeling, SAM, which was used to calculate total generation and response, and ReOpLite, which was used to model the system's resiliency. In the main graphs above, we can see the system's circuit diagram before and after the addition of the system's PV and battery storage. And on average, the system can offset about 119% of the university's load, with the additional generation going to batteries. In this section, we can see the impact that the additional PV and battery have had on the grid. These graphs show a significantly large increase in the power and voltage of the system's overall operation on the mainland connecting the university and the substation. All the analysis was completed using OpenDSS, using its PV, battery, transformer, and smart inverter elements to model the system's operation. Unfortunately, when completing this section, we were only able to model the system for about 2,000 hours. This was due to a floating point error that occurred at hour 2058 that was caused due to the system's smart inverter selection. And due to time constraints, we were ultimately unable to debug this error in time and only completed the analysis for a smaller section of time.
our battery optimization, we found that by designing a system that was double our PV system size, the batteries would be charged to 50% at all times and be most optimal for our system. By implementing batteries, our system can level out the duck curve and reduce the university's energy bill. The system can also sustain 100% of the critical load from the given data for at least 2.5 days. As seen in the graphs on the left, the peak resilience months are from January through April, and the discharge cycle will be above 60% for the majority of the year. Finally, the PV system and batteries can serve the load without the grid. However, the system cannot sell back to the grid.
Looking at the cost analysis of what this system would entail, for all the panels, inverters, transformers, and batteries, coming out to $62 million. When you include labor of installation for this, the total now becomes $76.5 million, including the development of permits and clearing the land and figuring out a construction company, being an $84.5 million project. And then with the reserve from the Crest Financial tool giving us $5.6 million, a total cost of this system would be $88 million, or $2.52 per watt DC. Looking at the loans and taxes and for this type of system, the loan for the school that they would need for is roughly around 50% of the total cost. The loan would then incur for 15 years with a 7% interest rate, with a minimum debt service coverage ratio of 1.2 and an average DSCR of 1.5. The cash flow analysis chart to your right shows the break-even point around 6.5 years. And then looking at this graph and the one on the slide before, this shows that the total revenue over the 20-year period would come out to be $242.5 million, where the total system profit is $66.4 million, and the average total system profit per year is $3.3 million.
Next is our development plan. First, we look at the construction plan, which we required with the competition to take at least 6 months. We broke this down into 4 phases. The first being the solar assessment, which will take an estimated 1 to 2 weeks to determine if the land is viable for solar and begin obtaining the necessary permits. The second phase being the design and engineering with an estimated time of 6 to 8 weeks. This phase includes the solar design interconnection approach and the battery optimization. The third phase is the procurement and construction, which would take an estimated 6 to 10 weeks, but could take longer due to the size of our system and equipment demands. Finally, we have the commissioning phase, which includes all necessary electrical and structural inspections. Next, we looked at several different compliances with our system. First, for the zoning compliances, we were told to assume that all land considered as commercial and already zoned. However, the panels and mounting on the roofs do need to comply with New Mexico's visibility standards. Next, we look at the compliance with New Mexico State's district plans. Some disadvantages to our project would be the removal of Milton Hall, Mongoli Hall, and the addition on Breland Hall. However, we chose to still place solar on Milton and Breland. Some advantages for the project are the renovation of the College of Education and Zoo Library and the additions of a new business complex and graduate school, which would allow for more potential PV systems. Additionally, this design will meet the university's sustainability goals. Finally, we were asked to comply with several different building regulations and codes. We were told to assume that the systems that we created and building structures would pass the necessary inspections. Additionally, the permits would need to be acquired for the electrical clearing and construction.
For the buy-in strategy for New Mexico State University, points that would be made to the district decision makers would be that it would reduce the overall cost of the university and create new academic opportunities for current and prospective students, to engage New Mexico State University's community members. This would be done by promoting clean energy efforts for the university, around campus and more educational opportunities.
So now a summary of the innovation and optimization. Overall, we created a high penetration renewable energy system that added 13 new PV systems across campus with an additional 55 utility scale batteries. In total, the system can sustain itself for about 2.5 days and provide a 119% offset of the university's typical load. By adding the system to the New Mexico State University campus, we'll bring in a beautiful human-focused design that allows for students and visitors to witness and interact with the future of energy firsthand. This would allow for the university to gain increased enrollment as well as new research opportunities. With this system, we will not only see New Mexico State University becoming a leader in sustainability, but also living up to its motto of being bold and shaping the future. We will now open the floor to questions.
Great. Thank you, Team Marquette. That was excellent. So yes, over to our judge Q&A session. And without further ado, Toya, I'll offer you the first question.
Sure. I think you guys did a really good job. I, for one, really appreciated the renderings for the solar structures in the quad. I thought you did a very unique job at that, and there's a lot of innovation there. So just a quick question on emissions. Did you guys consider the impact on emissions and what that reduction would look like?
I can answer that. We didn't necessarily look at the emissions themselves, but we do believe that they would reduce them. I guess, Darren, do you have anything to say about that?
Not too much extra, just that overall, the emissions created from the actual development of the system would be greatly diminished by the actual amount of emissions that it would save from the generation itself.
Okay, thank you.
All right, thanks so much. Mike, a question for you.
Great, thank you. Good job, team. I got to say, I've looked through several documents and still wasn't sure exactly what size battery system you recommended, but they look like some of these are pretty large. But my real question has to do with clearly some of the challenges that you saw with using the OpenDSS model, and it sounds like it was blowing. I've heard these kind of stories from many people that sometimes you run a model that could run for a day and then crap out and just fail. So could you describe maybe a little bit what some of the challenges were with the model, and perhaps any recommendations you might offer back, for future events, like would some kind of a better resource for guidance on the modeling be helpful? I know it can be difficult, but anybody who worked on the model, could you address that?
Yeah, so we definitely had a lot of issues with OpenDSS. Mainly it was more of a, we didn't really know how to use it. So yeah, providing more guidance on how to use the software would have been a great resource. But yeah, we had tremendous issues, especially setting up the smart inverter system itself. We believe that it may have been due to only having created one smart inverter element rather than an individual element for each PV system itself. So after running the system, it did take about a couple of hours, and then at the very end, it just provided a non-specific error, which eventually we determined to have been caused by the inverters themselves.
Well, great. I think your comments in your report will be kind of taken to heart, that perhaps there should be more resources, because modeling is a challenge even for the best of electrical engineers. So thank you for your response. Thank you. Good job.
Thanks so much. Chris Lord.
Yes, like Toya, I really liked your innovative use of the horseshoe quad there with, and particularly the renderings. The picture's worth 1,000 words, and I could see it, and I very much liked that part of the proposal. On the economic side, I was, like many of the teams, I felt like I received more conclusions than the actual model to help me understand them. And I must say to all the teams, if you're dealing with a sophisticated client like Patrick, for example, or a CFO, they're going to want to know why and how your model works so that they can understand and appreciate the either accuracy of it or have their own observations. But in your case, I saw the PPA price is 30 cents. And given the university's current cost of power, I wasn't sure I understood how you could project savings for the college and how that worked mathematically. And so perhaps you could kind of help me understand a little bit better how the university could justify a system where they're paying almost 10 times higher price. I think the average price at the university was in the 3 or 4 cent range, and how that would work.
So for the PPA price, we didn't necessarily look at it too hard. We really wanted to, I guess in the way that you stated it, find the conclusions to the system, as we do not have a very strong background in the financial analysis area. I would say that yes, paying about 10 times more is quite excessive, but we felt that from the maximum profit that we gained in the project that was outputted to us, we felt that it was a viable system. Does that answer your question?
That was a good shot at it, I will say,
Okay.
to get your candor. And maybe for you and all the other teams, having an economics major pulled into the project might be good for the future as well.
Mm-hmm.
But thank you.
Great, thanks so much. Next question, Evan, over to you, and then following Evan, Patrick, you may ask your question.
Yeah, so great job on the development and construction plan. I found it comprehensive, thoughtful, and the schedule pretty realistic. Just one item that I didn't see called out was the method by which you would evaluate and select a construction contractor. Maybe can you take a moment and talk through the timeline and process by which you would do that? Because I didn't see that part specifically called out in the plan.
Yeah, so the contractor would come in after the solar assessment. I didn't specifically state it there, but we developed our construction plan based off of talking to our construction management professors at Marquette and kind of gathering what would go into a construction plan and then forming it from there. But in terms of going about choosing a contractor, I'd say that it would fall right after the solar assessment and deeming what was viable so that they could choose a company that could handle a size system like this.
Excellent, thank you.
Okay, my turn. So let me just tell you, I just love your artistic renderings. I think you really picked up a lot of the essence of the Southwest region, and quite honestly, I'm prepared to share these with our campus architect. You may see one of these erected up on our site. I thought those were amazing. So the one thing to keep in mind, I did notice you utilized the quad, and although it was allowed to develop something, just go back and read that part, because it says you could use the quad, but just don't use the open space of the quad. And that's because that's where the marching band practices. And I used to be a music major when I went to school, so that's kind of a big deal for me. But I mean, otherwise, those are sizable units that you could practically relocate those anywhere else. So it wasn't like a major structure I was too concerned with. But I want to figure out, it looks like you really designed for almost full resiliency, 100% for 2.5 days. And I'm wondering why you chose 2.5 days. And if you knew about our cogeneration system, that we actually produce around 50% of our in-house power. We do take gas at 400 PSI, so we get a really good natural gas rate. But I wonder if you would still design around that if it wasn't a consideration, that you'd go for the full 100% for 2.5 days, knowing that we already have about 50% of emergency power already.
Yeah, so in our resilience analysis, the way that we ran our analysis is we ran multiple versions of it in which we tried to maximize how much resilience we could get back at 100%, 50%, and how many days. We did not know beforehand that you generated your own power, so taking that into consideration, we would have adjusted our our analysis to 50% and seeing the outputs from that and maximized for the 50%.
Can I pose a question?
Okay, thank you. Great job.
Can I pose a question on behalf of the team back to Patrick?
Yeah.
Have you got a black start capability with that system, Patrick? Are you able to, if all the power went out on the campus, do you have the energy you would need? And where does that energy come from?
So you're talking about the cogeneration system. Yeah, we do have black start capability. We do have a direct feed natural gas from, we actually collaborate with a local municipality. We kind of bundle our gas consumption with theirs. They get a really sweet price. We're about 40% of the natural gas consumption of all of Las Cruces due to our cogeneration. But, we do have some resiliency there in being able to leverage the gas versus the electric. But yes, we can do a black start. We got about 4.5 megawatts on demand.
All right. I thought that was a place the team could have come back with their 2 days, but okay, thanks.
Great. Good job, teams and judges. Congratulations on getting through all of these and doing them all so well. We have another 30-minute break lined up, so feel free to stretch and take